probably will. I'm just afraid that by the time I get there, it's going to be over.
I was telling you about the process by which you can take a carbonyl compound and carry out an alpha halogenation. And I remember telling you that this type of reaction, at least one form of it, is a diagnostic test for methyl ketones, because if you have a methyl ketone, you get iodoform. And iodoform is a yellow crystalline substance. It's a canary yellow substance. And somebody told me, I don't know if it's true, but they said the local pet store is sold out of canaries. So I guess many of you wanted to find out what the colour of iodoform was. That's what I told you at the end of the last lecture. And what I want to do now is to show you how this alpha halogenation, because if this is a carbonyl, that is the alpha position, and if you've got a carbonyl system, say like this, one of these would be the alpha, then the beta, then the gamma. This would be alpha prime, beta prime, gamma prime, and so on. And if you wanted to, you could call this one alpha, beta, gamma, and this would be alpha prime, beta prime, gamma prime. There's no rule, you just do whatever you fancy. The alpha position is the position next door to the carbon that is the carbonyl carbon. And the beta position is one removed. The gamma is one removed further. So all these reactions are alpha chlorinations or brominations or halogenations, and they all go either via an enolate or via an enol. And what I want to do now is to show you an application of this process to carboxylic acids. Now, carboxylic acids have a carbonyl group, as you well know. And for carboxylic acids, provided you do the reaction in the right way, which is a bit more complicated than this, you can put a chlorine or a bromine in the alpha position. So you end up with an alpha chloro or an alpha bromo carboxylic acid. And those things turn out to be useful because you can convert them to other things, including amino acids. And amino acids, if you've taken any biochemistry course, or even if you've never taken a biochemistry course, but you read the newspapers or cookery books or something like that, you will have heard of proteins. And amino acids are the constituents of proteins. So let me show you how to carry out an alpha halogenation of a carboxylic acid. Now this reaction is named after three people. It is called, let me just get a fresh pen, that's rubbish now. This one is fresh.
Is it Volhard? Volhard. Volhard.
It's called the Volhard-Zelinsky reaction. Zelinsky was a Russian chemist. Volhard was a German chemist. The other guy, or the other word, is where one goes if one doesn't learn chemistry. Carl Hell was a German chemist. So these people worked out a way of converting a carboxylic acid into an alpha halo carboxylic acid. So the general procedure is this one. They take a carboxylic acid, and here is the alpha position which I've labelled, and they treat it with a halogen and red phosphorus, and then with water. And if you do that, you get the alpha halo acid. And the halogen is chlorine or bromine. I don't know if it works for iodine. I've never seen it for iodine. Now, how does this work? This is not so simple. What happens is that, let's do it for bromine. Bromine plus phosphorus gives you phosphorus tribromide. Now, if you take a carboxylic acid, let's write one here, and you treat it with phosphorus tribromide, what you get is the acid bromide. And if you treat the carboxylic acid with phosphorus trichloride, what you get is the acid chloride. It's one of the ways of making an acid chloride or an acid bromide. Now, in this process, you also generate some HBr. Well, we don't have to worry about that. Let me change this. This compound now enolizes. And that acid bromide enolizes much more readily than the parent acid. Now, if you have the enol, and there is bromine present, you know from what I told you the other day that you will get an alpha bromo compound. And finally, if you put all that into water, you will hydrolyze the acid bromide and get the acid. Now, one of the reasons why an acid bromide enolizes much, much more readily than the carboxylic acid is that the acid proton in the carboxylic acid is removed preferentially as opposed over the alpha position. The hydrogen on the carboxylic acid oxygen is removed in preference to hydrogen in the alpha position. But in an acid bromide, there's no hydrogen on the oxygen, and so the enolization occurs. There are other factors as well that make this position for an acid bromide more acidic than for an acid. So that's why you make the acid bromide. You make it in situ. That just means in the flask. You don't make it separately and isolate it. You can if you want to, you don't have to. So you get rid of this proton, and at the same time, inevitably get rid of that oxygen. You make the bromide enolizes. The enol then is brominated in the usual way, exactly as I described for the polar reaction and the other alpha halogenations. And now you get an alpha bromo acid bromide. And you know that if you have a leaving group on a carbonyl, and you treat that with a nucleophile, in this case we use water, the nucleophile attacks the carbonyl, the electrons go onto this oxygen, sometimes it's protonated here, but in any event, a pair of electrons comes back and expels the leaving group. Then if you follow that through, you then end up with the alpha, in this case bromo, carboxylic acid. And if you use chlorine and phosphorus, the same sort of thing happens. And so this is the Helm-Vollard-Zielinski reaction. And the reason why it's named after three people is one guy invented it, another guy made an improvement, somebody else made a few more improvements. So that's the story for that. Now, I told you that the reason for anybody being interested in these compounds is that you can convert them into a load of other substances. So let me just show you one of the substances that you can convert these things into. Supposing, I'll clean the board.
Why would he leave that there? Why would he leave that there?
If the digging walks in, he'll think I'm giving a lecture on theology.
He's so random.
Okay, I want to show you now a use of alpha halo acids. Supposing I take an acid, let's just take this one. Oops, let me write that more neatly. I can now make an alpha hydroxy acid. Because in the alpha position to the carbonyl, there's now a hydroxy group. And the way that that has happened, you can work it out yourself, I'm sure, but just for completeness, I'll put it on the board. It's an SN2 displacement. Now it turns out that SN2 displacements at the alpha position of alpha halocarbonyl compounds, of which this is one, those SN2 displacements are very easy. They occur much more easily than if the carbonyl wasn't there. And there's a reason for that. I'll just give you roughly a hint as to what the reason is, because I don't want to get into details beyond this course. If you look at this, single, single, double, you look at that order of bonds, single, single, double. Now if you look at this alignic system, single, single, double, and you know something about alignic systems, you can carry out an alignic bromination. And if you've got loads of other bonds here, let's say the bromination occurs only in this position, alignic bromination. It doesn't occur here in the standard way that you do the reaction. So there's something special about alignic carbon to something else bond. And guess what? This is a sort of alignic system. Single, single, double. So there's something special about this bond. What's special is that it isn't as strong as if the carbonyl wasn't there. If it isn't as strong, you can kick it out more easily. You can displace it more easily. So nucleophilic substitutions, SN2 reactions, of alpha halocarbonyl compounds go more easily than if the carbonyl isn't there. Now you don't have to worry about the reasons, but I just wanted to make it clear to you that it isn't magic. It all makes nice sense. So you can take an alpha halo acid and convert it into an alpha hydroxy acid. If you take, where's the cleaner? Here it is. If you take an alpha halo acid, let's say, let's do a different one. and you treat it with ammonia, and if you treat that, well, let's leave it as it is. This is an alpha amino acid. And if you treat that, say, with HCl, what you will get, and you will see later on, probably not in this lecture, this is alanine hydrochloride. And alanine is one of the amino acids. And this stuff, from the way that I made it, is racemic. Because you see, here is an asymmetric center. So there are 4 things attached to this carbon. A methyl group, an NH2 that's protonated, we'll talk about that probably in the next lecture when I deal with amines, and a carboxyl group. So there are 4 things attached to this. And you know, whenever you have 4 different things attached to some carbon, then the substance is chiral. It can exist in 2 forms. One has the R configuration, the other one has the S configuration. But when you make a chiral substance, from a substance that isn't chiral, and we made that bromide from a compound that isn't chiral, because there's no bromine there, there was just a CH2. When you make that bromide, the bromide's chiral, but it's racemic. So this is racemic, so that is racemic. So you have a racemic amino acid. And this is one of the ways of making amino acids. Now I'm going to change gears somewhat. I'm still going to talk about enols. But I'm going to tell you something else about enols. What I've told you so far in the last lecture is that if you've got a carbonyl compound, it can enolize depending on what the carbonyl compound is. The amount of the enol present in the material can be very, very small, or it can be very large. In the case of beta dicarbonyl systems, you can get very extensive, a very extensive amount of enolization, because I drew up a 6-membered structure that will stabilize the hydrogen bond for beta dicarbonyl compounds. That's what I told you. Then I showed you how if you make some enols by acid catalyzed enolization, or if you make some enolates by base catalyzed enolization, you could do something with those enols or enolates, and the thing that I told you could do is you could brominate or chlorinate or iodinate them to get ultimately alpha iodo or alpha bromo or alpha chlorocarbonyl compounds. And in the case of methyl ketones, you can make iodoform, this canary yellow solid, which its formation is a diagnostic test for the presence of a methyl ketone. And then what I've just done now is to show how you can make an enol from a carboxylic acid by first converting the carboxylic acid into the acid chloride or bromide, and then adding either bromine or chlorine. Then hydrolyzing the acid chloride, so you can make an alpha halo acid. And I've given you 2 examples of the use of alpha halo acids. You can either make an alpha hydroxy acid, or you can make an alpha amino acid. I'm now going to tell you something else about the business of enolization. What I'm going to tell you is how to make a very high concentration of an enolic species. And the species that we're going to make is going to be an enolate. If you take a ketone, say acetone, it's almost 100% keto form, but you can convert it into 100% enolate form in a special way. And once you've got that enolate, you can use it to make some additional compounds. In particular, you can use it to make some carbon-carbon bonds. Let me show you how that's done. If you take a ketone and you treat it with a suitable base, and I'll have to tell you in a moment what a suitable base is, then you can abstract one of the hydrogens from the alpha position, and if you follow through the little curly arrows, you can see that you can generate an enolate. Now, what is a suitable base? There are some requirements of this base. You know from a previous lecture that if you have a nucleophile, it can attack a carbonyl. I showed you hydroxylamine, I showed you hydrazine, I showed you a few things that can attack a carbonyl. You don't want this base to attack a carbonyl. You want to attack a hydrogen. So one way to prevent attack at the carbonyl is to make the base very big. The other thing that you want is, because these hydrogens are not terribly acidic, you want the base to be a very strong base. So you want a strong, hindered base. And there is one compound that, well, there's more than one, but the famous compound that satisfies those requirements is made from this amine. This is called diisopropyl amine. Diisopropylamine. And you can see it's got two isopropyl groups, so it's hindered. And what you do is you treat it with butyl lithium. You treat it with butyl lithium. The butyl lithium removes the hydrogen to give you this compound, which is lithium diisopropylamide, abbreviated as LDA. So LDA is among organic chemists is a very famous base. It's a strong base. It is not nucleophilic because it's hindered. It's basically too fat to squeeze into this position, so it doesn't do nucleophilic attack, but it's a strong base, and so it removes a proton. So if you have a ketone and you treat it with LDA, you make LDA in a flask, you take a flask, you put in some diisopropylamine, you add the appropriate amount of butyl lithium, which you can buy. If you don't want to make it, you could buy it. The butyl lithium will remove this acidic proton. Remember that hydrogens on a heteroatom, that means hydrogens on nitrogen, hydrogens on oxygen, hydrogens on sulfur, they're fairly acidic. Then you get LDA, and the LDA pulls off the proton alpha to a ketone. So let's now see what you can actually do with that experimental technique. So I will clean the stat board. So I've got a ketone. This ketone has a methyl group next to the carbonyl. So it is 2-methyl cyclohexadiene. X and O. That much I'm sure you all realise very easily. And I'm going to treat it with LDA. Now I've told you that LDA will remove an alpha proton. So what are the possibilities? I've got 2 alpha protons here, and I've got 1 alpha proton there. So straight away, I'm faced with a problem. Which of those alpha protons, the one on the left or the ones on the right, will it remove? Now I've given you a clue. I said that LDA is a hindered base, and therefore it cannot easily get into small areas, which immediately tells you that these 2 hydrogens are going to be more accessible. And so of the hydrogens on the left or the right, that it in principle could remove, if you do the experiment properly, it will remove only the hydrogens on one of the hydrogens on the right. It doesn't matter which one. So that's what happens. You get an enolate. Now you have to do this experiment in the right way. What you have to do is you have to take one equivalent of LDA, put it in a flask, and add to it at a low temperature, and add to it dropwise one equivalent, or 0.99 equivalents, of the ketone. And that's the only way that this will happen. If you add an excess of the ketone and stir it for a little while, what you actually get is this double bond over here. But we won't go into that. That's way beyond this course. All that I want you to know is if you add a ketone, an symmetrical ketone is no problem. But if you add an unsymmetrical ketone to LDA, the less hindered side of the carbonyl is the side that's deprotonated, unless the substituent on the other side is an activating substituent that makes this hydrogen so acidic that it will be removed preferentially. But that's not going to happen in your course. It won't happen in the exam either. So, this is what we get. We can make a particular enolate from an unsymmetrical ketone. You can also make an enolate from a symmetrical ketone, but that's child's play. Now, what can you do? What can you do? What can you do with these enolates? Well, what you can do is you can make carbon-carbon bonds. So let me show you how to make a carbon-carbon bond from that type of enolate. If I now add methyl iodide, the electrons can move here, they can move like that, and I will get this plus lithium iodide. So what I've done is I have made a carbon-carbon bond. Now this thing, as I've drawn it, looks reasonably simple. It's actually fairly complicated because one thing I haven't dealt with is what's the relative stereochemistry here and here. Because these 2 methyls could be pointing towards you, or one could be pointing away from you and one towards you. We won't deal with that. That we don't have to know about. It's not so simple, even at a research level. It's not so simple. If, for example, instead of using methyl iodide, I would use benzyl bromide, then what I will get would be that. And you can see now that by this process I can take some compound and I can make it in one step into something that's a heck of a lot bigger and more complicated. So the formation of enolates is very important in making carbon-carbon bonds and in constructing pretty complicated molecules. And I will work through now an example that shows you how this can be done. Supposing, I'll give you a moment to just copy that down. Some of you do not seem to have taken speed writing, whatever that may be. I see that at times. It's probably load rubbish. So speed reading, that's definitely rubbish.
I didn't mean it. I know you. Do they like hurt your burner?
It starts to feel really uncomfortable. Like your eyes are suffocating.
Yeah, they're kind of going out. Just a little bit.
Like I've done it before, it gets uncomfortable.
Aww.
Supposing I want to make this compound, for some reason, maybe it's got a nice smell, I don't know, but supposing I want that compound for some reason, I notice that it is a ketone, so I can ask myself, what ways do I know to make ketones? I notice it is an olefin, an alkene. I could ask myself, what ways do I know of making alkenes? Turns out, if you think about it for a while, the most profitable question to ask is based on the fact that you notice that it is a ketone. What are the ways are there of making ketones? Well, one of the ways is of making complicated ketones, one of the ways is to alkylate a less complicated ketone. And so, on that basis, I'm going to ask myself, is there some carbon piece that I could stick onto a less complicated ketone so that I would make a bond to make this more complicated one? And the best answer is if you think about making that bond, because this ketone here happens to be commercially available. And there's a load of it down in the stockroom in this department. So you could go and get some. Is there some method that I know for sticking that piece onto here? Well, yes, there is. Because if I can make an enolate, then the electrons could come like this, and that would then give me the product. And indeed, if you treat that ketone with LDA in the way that I've described, it will be deprotonated at the least hindered center, least hindered carbon, adjacent to the carbonyl. And so although looking at the target molecule, the one on the far left, just looking at it, you might think, this is a horrendously complex problem, how could I possibly make that stuff? There are numerous ways of making it, but based on what I've been telling you today, a very good way of making it would be by alkylation of an enolate. And whenever you see a ketone, obviously until today, if you were asked how to make it, you would probably think in terms of oxidizing alcohol. And then you can ask yourself, how can I make suitable alcohol? And in fact, if you want to do that, that's fairly straightforward. Let me write the parent alcohol of that. So that would be the parent alcohol. If you oxidize that alcohol, you get a ketone. How could you make this alcohol? Well, there are several ways. If you took that Grignard reagent and added it to the aldehyde, that's what you get. And this is a known aldehyde. And the bromide that you need to make that Grignard, you can get quite easily as well. So even for a simple compound, I've shown you a couple of different ways. There are loads of other ways. We won't go into them. I just wanted to show you that when you have to make a particular target compound, one of the things that you need to do is to try and recognize pieces of the compound that you know how to assemble. If you see a ketone, you know in principle, one of the ways to oxidize an alcohol. And so the question is, how do you make that alcohol? You also know if you see a complex ketone, one of the ways of making it is to alkylate a less complex ketone. So those are two approaches that I've given you. Of course, there's another possibility. Supposing I were to break this bond, what I would need, this is clearly beyond the course, I need that organolithium or Grignard reagent, because it could go into an aldehyde here, still get the same alcohol. So even for a fairly simple compound, there are loads of ways of making those compounds. Now what you should do is you should do problem number 18.6, which is equivalent to problem number 17.3 in the 9th edition. Now, what I've done so far is to give you a very, very little bit about the business of taking a ketone, deprotonating it with LDA, and then carrying out an alkylation to make a more complicated ketone. This business of alkylating an enolate, in that sense, it's very, very important, but there's one other related enolate alkylation, and that is the use of beta-dicarbonyl compounds. So I've talked about an ordinary carbonyl compound, a ketone. I'm now going to talk about alkylation of beta-dicarbonyl compounds. So these things have got two carbonyls, and they're 3 atoms apart. Let me show you what I mean. One of my group members is trying to make this ketone.
Like if I didn't know it, I'll be like, he's valid, and she knows
Think of it that way.
that. It looks so weird. Make you look like you want to kill me. That's true. Oh. Stop. Okay, sounded more natural this time. Many things.
If any of you have got any good ideas to help us, that'd be much appreciated. It'd be much appreciated. Not easy to make this ketone. Not easy. It'd probably take us about 30 or 40 steps if we succeed. We're getting close, but making ketones is not just something that the textbooks describe just to torment you. People actually do make ketones, sometimes very complicated ones. Let me show you this business of beta-diketone. Don't write this down, it's just to relieve the intensity of the discussion.
I'm just gonna finish it.
I didn't even start writing.
Nice. It's like you knew.
Yeah, no, I was just like, seriously?
So this is a beta-dicarbonyl compound. And if you treat it with sodium
It's too lazy to
hydroxide,
erase it.
what will happen will be this, for which I can write various resonance structures. I'll just write one of them. If you take this compound and treat it with an alkylating agent, what will happen will be you will get alkylation occurring exactly as I described for the enolate of cyclohexanone. There's nothing funny about this process excepting that the alkylation of beta-dicarbonyl compounds, generally speaking, works very, very well. And it's very tolerant of sloppy experimental technique, whereas the alkylation of a ketone sometimes doesn't work so well, and it's not tolerant of lousy experimental technique. So this reaction goes very, very easily. Now, why do people want to do this? Well, what they often do is they will take this compound and they will treat it with aqueous sodium hydroxide. And if they treat it with aqueous sodium hydroxide, what they will get is the salt of the parent acid, because all that the aqueous sodium hydroxide does is to hydrolyze the ester. You remember a few lectures ago I talked about hydrolysis of an ester. I did hydrolysis of an ester, hydrolysis of a nitrile. You get the salt of the acid. And now, if you acidify this, you get beta-keto acid, and when you heat a beta-keto acid, it decarboxylates. So now, plus CO2. So now you've got a ketone. So this is yet another way of making a complicated ketone. Instead of starting with a ketone, suppose starting with acetone, and making the enolate and then adding this piece by alkylation, what you start with is something containing another functional group, the ester. You then alkylate that, and then you get rid of the ester group. So this looks like a long way round to make this compound, because from what I told you before, you could take acetone, make its enolate, and alkylate it. So why do people do this? They do this because the alkylation of beta-dicarbonyl compounds generally works so very well. And it's more economical in terms of yield to go this route than to go via acetone, in this particular case, deprotonate it and alkylate it. Now, you notice something. This compound has still got a hydrogen here. And so, of course, you could deprotonate it again and alkylate it again. So you could put two alkyl groups. And if you then hydrolyze the ester, you now get another alkyl group there. Let me show you a work example, and then I've got only 4 minutes, haven't I?
Yeah, that's the thing. That's the final. What's the last?
How many more lectures have I got?
Six?
Three?
Six.
Six? About six. Oh, that's plenty. That's marvelous.
That's what he asked.
There must be a lot more to learn. He has less than 6 more hours. Yeah.
Yeah, right.
Well, he goes really quick with you though.
Supposing I wanted this compound.
I like that idea.
There are several ways I could make it. If I wanted to use the beta dicarbonyl system that I've just been talking about, I would take this substance, I would then treat it with sodium ethoxide, the hydrogens here are very acidic because they're flanked by 2 carbonyls. Remember that I told you at the beginning of today's lecture that the alpha hydrogens, the carbonyl compound on the ketone, are acidic, and with a strong base you can remove them, and the strong base that's preferred is LDA. Well, the hydrogens between the 2 carbonyls are much more acidic because they're flanked by 2 carbonyls. And a weaker base, like sodium ethoxide, is perfectly satisfactory. Sodium ethoxide is easy to make. You take ethanol, then you add some sodium to it. One of my former students told me, who came from Russia, he told me that many, many years ago, when he read the Russian literature, you found very, very few examples of crystallization from ethanol, or experiments in which ethanol was used as a solvent. The reason for that, according to the student, was that they had something better to do with the ethanol than use it for chemical purposes. But over here, we can use sodium ethoxide, deprotonate it, and then what we can do is to add ethyl bromide, and then repeat the business of deprotonation. And then add methyl iodide. Then hydrolyze it with sodium hydroxide. Then acidify. And that will give us
Not fair at all.
what's funny is a perfectly normal reaction. And then you heat it.
No.
And you lose carbon dioxide. So all this is a particular example of something that I told you 5 minutes ago. And it works very, very well. I've carried out some of these reactions as an undergrad on a large scale. I think I've given enough to today.
Thanks, Paula.